Okay, thank you very much, Somnath. So it's a great pleasure to accept the invitation that Somnath sent. I couldn't say no. So even though I don't really enjoy online talks very much, and I've been saying no to various online events recently, I couldn't say no to Somnath. Um, so I think what I'm going to talk more is the more a more appropriate title would have been what are L functions, or what I consider to be L functions. But since it's a what is series, I formulated it this way. The idea is I'll start with a very specific example, as you can guess what that would be, and say a bunch of things about them. Then I'll go on to say something about a very general class of L functions. And then I'll go back again to a specific, the specific example that we discussed first. So if you have any questions, you can stop me, or you can put it in the chat, although I don't see the chat because I just see the screen. All right. So, and I don't see any of you, so I don't see hands raised or anything. So it might be best if you just interrupt me and ask questions. All right. Okay. So as you can guess, the example that I'll talk about mostly is the Riemann zeta function. This is the first L function that was defined at least as early as by Euler, so 18th century. Most of the things that I'm going to talk about is 19th century mathematics, perhaps with a 20th century viewpoint. So even though this is the zeta function bears the name of Riemann, this was studied a lot by Euler, and you'll see that most things that I say today are due to Euler actually. So it's defined as this infinite series, summation 1 over n to the s, where s is well, firstly, if you could just say s is a real number bigger than 1. There's no need to restrict it to real numbers. Maybe this is one thing that Euler did not realize, that you can because of the time period, that you could actually do some complex analysis, and so you could take s to be a complex number. He was basically restricting to real numbers. Okay, but there's no need to restrict to real numbers. You can take any complex number, and this series makes sense if the real part of the complex number s is bigger than 1. At s equal to 1, we know that summation 1 over n diverges. Right? So you can use you can compare it with log integral of log x, integral of 1 over x, and so on. Okay, sorry. All right. So, okay. More generally, we could consider what are called Dirichlet L functions. So, sorry, my nose was bleeding a little while earlier. So, okay. So I can take a Dirichlet character. So it's simply a group homomorphism from Z mod AZ star to C star. Okay. So I take all the elements in Z which are co-prime to A and take its class modulo A. That forms a group under multiplication, and I just take a group homomorphism from that group to C. So don't worry if you haven't seen this. We'll just restrict to Riemann zeta function, but I just wanted to give one more example before I say specific things about Riemann zeta function. Okay. Then I can extend it to a function from Z to C. Well, there's a map from Z to Z mod AZ. And how do I extend it to Z mod AZ? Whatever is not a unit in Z mod AZ, I just define chi to be 0 there. So that's why this takes values in C and not C star anymore. That's the extension. That's a standard way to extend characters to Z. And you can define the Dirichlet L function L chi S as summation chi n over n to the S. Okay, so so this definition doesn't quite make sense without me telling what the convention is when A is 1. So when A is 1, every the extension it just takes value 1 everywhere. Okay. Uh, so this GCDN comma A not equal to 1, that part kind of is not quite accurate when chi is the trivial character. But with that convention, if chi is the trivial character, and if I put that convention, then this L function, Dirichlet L function, reduces to Riemann zeta function. Okay. So these are two of the earliest L functions. Okay. So Euler started studying zeta function to solve this problem that had been posed. I think it's called the Basel problem, BASCL. That's a town. So the problem was to find summation 1 over n squared. Okay, and Euler not only solved that problem, he also found summation 1 over n to the 2k for any positive integer k. So he found values of zeta function at all even positive integers, as I'll say later, as I'll show you later on. Okay, so but then he was very fascinated by this function, and he kept uh, kept coming back to it all the time. So one thing that he noticed was this product formula. Okay, so this is called Euler product. That's why. So summation 1 over n to the s. Formally, you can see that if you expand this product, 1 minus 1 over p to the s inverse. So this is 1 minus 1 over p to the s inverse is just 1 plus 1 over p to the s plus 1 over p to the 2s plus 1 over p to the 3s and so on. And if you take product over all primes, then formally, at least using the fundamental theorem of arithmetic, you get this sum. Okay, you get the usual sum that that defines the Riemann zeta function. And for real part of S bigger than 1, everything is absolutely convergent, and so you can actually make this proof rigorous, and you can actually make it into proof. You can make it rigorous, and you get this product. Okay, so this is called Euler product, and we'll see that for something to be called an L function, this will be a necessary condition. Okay, so later on, what I'll do is I'll say we want to study an abstract class of functions, which we'll call L functions. So when some complex analytic function deserves to be called an L function, and so it has to satisfy these properties that I'm telling you about Riemann zeta function. So the first of them is the Euler product formula. Okay, already the Euler product formula is quite useful, and Euler noticed the following. Okay, so yeah, before we move on, similarly there is an Euler product for Dirichlet L functions. So this is, at least formally, you see that this works, and again you can make it rigorous because chi of p is just a root of unity. Right? Chi was a Dirichlet character. Okay, so Euler used it to prove that there are infinitely many primes. Okay, of course, Euclid knew that there are infinitely many primes, and that's the proof we first study about infinitude of primes. But as I mentioned during the previous slide, zeta of 1 is infinity. Okay, so zeta s has pole at s equal to 1. Therefore, this product on the right hand side, this thing, cannot be a finite product, and that's how Euler deduces that there are infinitely many primes. Okay, of course, he gets much more than what Euclid could get. And I did not write this out, but let me just say this orally. So if you take this, if you put s equal to 1 here formally in the in equation 1, then you get yes. So and you okay. So first you take log of zeta of s, and so you get log of zeta of s is minus log of 1 minus p to the minus s, and then you approximate that by the by 1 over p to the s, and forget about the higher order terms, which will be small anyways. And so when s approaches 1, you get that summation 1 over p diverges, right? So so not only did Euler prove that there are infinitely many primes, but he kind of proved that there are they are in some sense quite densely packed, right? So if you take summation 1 over n squared, if you take the sum of reciprocals of squares, you know that that thing converges, whereas the sum of reciprocals of prime diverges by Euler's proof. So in some sense, Euler is proving that there are many more primes than there are squares. Okay, so that's already quite something, which Euclid couldn't do. All right. So that's one property about zeta function. The second important property, and this is where Riemann comes into picture, although Euler again knew that this, I mean, he did not have the language, but he kind of knew that this should hold. And I'll tell you why. Okay, so even if you don't know complex analysis, what analytic continuation means is that you can complex analytically define this zeta function. So a priori it is only defined in the right half plane where real part of s is bigger than 1. But you can extend this definition beyond this line real part of s equal to 1. So you can define it basically everywhere in the complex plane, so that on the right hand side, when real part of s is bigger than 1, it matches with the Dirichlet series definition, and on the other side it is a priori a bit mysterious. Yeah, okay. So it can be defined for all s which is not equal to 1. And, a standard way of saying this, the jargon is that the term of art is that zeta s has a meromorphic continuation to complex numbers with only a simple pole at s equal to 1. Okay, so it has a pole at s equal to 1, and in fact it only has a simple pole at s equal to 1. Okay, so I'll give a proof of analytic continuation. This is kind of not the best proof, but it proves only analytic continuation. It doesn't tell you anything about functional equation, which I'll come to in a moment, and I'll not tell you anything about the proof of functional equation. So for that, I need to introduce gamma function. Okay, so gamma of s, this is defined as by this integral e to the minus t to the s minus 1 dt. Okay, so as long as s is not as long as real part of s is bigger than 0, this integral makes sense and gives a well-defined function. And it again has analytic continuation to meromorphic continuation to complex numbers, and one can show that it has simple poles at all non-positive integers. Okay, so 0, -1, -2, and so on. It does not vanish anywhere. Okay, so in particular, if I take reciprocal of gamma s, 1 over gamma s, it is an entire function. Okay, and it satisfies this recurrence relation. So gamma s you can obtain it from gamma s minus 1 by multiplying it by s minus 1. Okay, so you can take this as an exercise if you like, just integration. Okay, so what is the relationship with zeta function? Well, let me substitute for a positive integer n. Let me substitute um, u to be t by n. Then I get gamma s is n to the s integral from 0 to infinity of this thing. Okay. Yeah, I wouldn't even know if I get disconnected at some point, because I can't see the screen or anything. So I hope I'm still connected and you can hear me well. Okay, so
Yeah, we
gamma,
can.
yeah, thank you. Yeah, so gamma s satisfies this, and if I just rearrange it a little bit and sum over all n, I get the following relationship. Okay, so this is called an integral representation of zeta function, and all these things that are 17th 18th century mathematics, these are more or less the same kind of things that people still use to show analytic continuation, functional equation, etc. for this large class of L functions that I'm going to mention later on. Okay, so these are the first instances of these methods, and these have been these are being pushed to their limits to prove analogous results for L functions. Okay, so zeta s this is what is called integral representation of zeta s, and I should have actually written here that real part of s is bigger than 1. So this is still in the domain that zeta s was already defined, and we haven't actually moved to the left of it yet. Okay. Nevertheless, this integral representation is useful for getting analytic continuation, as I'll show on the next slide. Okay, so this is just copying what was on the previous slide. Okay, let me just rearrange that a little bit. So what I have done is I have used the formula for gamma s, which is s minus 1 into gamma s minus 1, multiplied both sides by s minus 1. So that's why I get s minus 1 times zeta s is 1 over gamma s minus 1 integral from 0 to infinity. And I have just taken the e to the minus, I've just multiplied the numerator and denominator of this fraction by e to the u, and I have taken one u from here and put it here. That's it. Okay, so this I have not done anything here except plug in the formula for gamma s in terms of gamma s minus 1 and rearrange things a little bit. Okay, so why is this? This right hand side is useful for me because it is what people had been studying then. So this is called Mellin transform, uh, and the way I'll normalize it is with this 1 over gamma s, and I'll define it like this. So if f is some function, to define it this way, I think it's enough to assume that this function has exponential decay. Okay, so it kind of goes to 0 faster than e to the minus lambda u, something like that. Right? So this function certainly has exponential decay. Right, so then I can define this Mellin transform, and again this is just integration by parts, so you can prove a couple of things about it. So the Mellin transform of f is minus 1 to the power n. So Mellin transform is a function, right? So it's a function in s. S is a yeah. So again, I should say s is here. Real part of s is bigger than 0. So this makes sense. This integral makes sense for real part of s bigger than 0. Okay. All right. So, but what you can show is that if f is a function with exponential decay, then any derivative of f is also, well, f has to be a smooth function, but if f is a smooth function with exponential decay, then any derivative of f is also a smooth function with exponential decay. You can define its Mellin transform, and you can show that the Mellin transform of f at S is related to the Mellin transform of nth derivative at S plus n. Okay. So in particular, because the right hand side in this one is defined for real part of S bigger than minus n, the left hand side also can be extended to the left of real part S equal to 0, right? So that's one thing. Great. So this is what will give us analytic continuation. But as Euler did, he went a little bit further, and well, you can also show. So both these are, you can take them as exercise. So this is, first one is just integration by parts. So you can do this, and the second one, at least formally, you can see how it works. Okay, so the Mellin transform evaluated at minus n will simply be the leading term of the Fn, right? So you just need to understand what the for an exponentially decaying function, smooth function, what the Mellin transform at 0 looks like. Okay, so 1 gives analytic continuation of S minus 1 into zeta S, right? This is using this. And 2 gives us the following. It gives us explicit formulae for values of zeta. Now that we have analytically continued it, well, what can we do with it? We can evaluate what the values are beyond this region where the Dirichlet series made sense, right? Where summation 1 over n to the s made sense. So in particular, you can ask, okay, what is zeta of 0, zeta of minus 1, zeta of minus 2, and so on. And this is what Euler proved. So zeta of minus n is minus b to minus this b n plus 1 is the Bernoulli number divided by n plus 1. So how are the Bernoulli numbers defined? Well, we just take this function as a power series in U, right? Because you see that this is U over U plus U squared by 2 factorial plus U cubed by 3 factorial plus U to the 4 by 4 factorial and so on. So in fact, it is 1 divided by 1 plus some power series in U, and so you can write it as a power series in U, and the coefficients appropriately normalized give you the Bernoulli numbers. Okay, so these are the famous Bernoulli numbers.
Sir,
And yes,
yeah, you said that you defined the Mellin transform for S greater than 0, right?
yes,
So how is property 2 well defined then MF minus N?
yeah. So because of 1, yeah.
Oh, okay.
Yeah, so 1 gives the analytic continuation of Mellin transform everywhere.
Right. Yeah. Thank you.
Yeah, thank you. All right, so these are the famous Bernoulli numbers, and in particular, the most kind of striking fact, and I mean, this was striking for Euler, and this is, I think, why he kept going back to it again and again, is that these Bernoulli numbers are rational numbers. Evidently, I just told you what the how to get the power series expansion of this. So you see that these are all rational numbers, Bn, and so these values zeta of minus 1 defined in this mysterious way by analytic continuation, they turn out to be rational numbers. Okay, so this is, I think, a very striking fact, and this is the kind of thing that I'm going to elaborate on in the last 10 minutes of my talk. And this is also the kind of thing that's close to my heart, because these are the kind of things that I work on. So values of L functions at integers, and mysteriously they often have these properties that they are rational numbers or algebraic numbers, or they are algebraic numbers up to something very well understood. So well, conjecturally at least. Okay, all right. So this was analytic continuation. And I promised that I'll tell you about functional equation. So here is the functional equation. I'm not going to prove it. So Riemann gave two proofs in his paper of this functional equation. And again, I must say that whatever proof that people still give for functional equation and analytic continuation for L function, they are they build on one of these, right? So so they build on one of these two proofs, even in general case. So you kind of try to use more general machinery and push these things forward. So for anyone wishing to pursue this subject, it's of course worthwhile looking at Riemann's paper. So here's the functional equation. Okay, so values of zeta at S are related to values of zeta at 1 minus S. Okay, so we kind of think that we understand zeta function to the right of the line real part of S equal to 1. Okay, because it's given by an explicit series. Now this functional equation tells you that these values to the right of real part S equal to 1 are related to the values to the left of real part of S equal to 0. Okay, uh, so there is of course this strip with real part of S between 0 and 1, which is mysterious, and people, you must have heard many things about this. So most famously the Riemann hypothesis and so on, which concerns about zeros in this mysterious strip. Okay, uh, also like even if you do, I mean, even if you don't have something as strong as Riemann hypothesis, but if you can show anything about zeros in this strip, you tend to get non-trivial results like prime number theorem and so on. Okay, but this is not what I'll talk about today, because yeah. So firstly, that's not the area that I kind of work in, and you may have heard of these things elsewhere. So we'll talk about something slightly different today. Okay, so I said about values at negative integers. Functional equation tells you what the values at even positive integers are. And the reason why we only get information about even positive integers is because gamma function has poles at integers, right? So uh, when we try to go to the other side with odd positive integers using this functional equation, we run into a pole of gamma function, and we can deduce nothing about zeta of 2n plus 1 for n bigger than or equal to 0. Okay, so yeah, so this is the problem that Euler solved and got a prize. Must have been a fortune at that time. I don't remember, but in any case, so he proved that zeta of 2 is pi squared by 6, and zeta of 4 is, I don't remember, something by 120 times pi to the 4, and so on. So he was really fascinated by the fact that zeta of 2n is 2nth power of pi times a rational number. Okay, and so what do these rational numbers mean? Okay, all right. Yeah, so here are some Bernoulli numbers. So B0 is 1, B1 is half, B2 is 1 by 6, B4 is minus 1 by 30, B6 is 1 by 42, and so on. Right. So if you notice, I don't have B3, B5, B7, and so on. And the reason is these are all zeros. Okay. So they are 0. And I went as far as B12 because the 691 is a very interesting prime, I'm not going to say anything about it today, but this is the this prime is related to Ramanujan's delta function that I'm going to say something about later on. Okay, very briefly. All right. So now, of course, there are conjectures about what zeta of 2n plus 1s are, and the conjectures are extremely strong. These are due to, I mean, the most general, in the most general form, they are due to conservation Zagier, which says that all these values are algebraically independent, and yeah, they are yeah. So in particular, they are transcendental as well. We don't even know transcendence of zeta 3. We just know that zeta 3 is irrational. That's all. So these are still very mysterious. Okay, zeta 3, zeta 5. There are various results about if you take first 7 of them, then maybe at least one of them is transcendental or something like that. I don't know. All right. Yeah. So now that I have said a bunch of things about our very particular L function, the Riemann zeta function, let me quickly jump to a big let me quickly jump to the most general kind of L functions that one would be interested in, at least from my point of view. Okay, so from a number theorist point of view. So these are the so-called Selberg L functions. So Selberg defined this class of L function at the beginning of 90s, and these are kind of maybe the most interesting objects to study, but everything is so conjectural about them, as I'll try to give an idea that this is more perhaps a guiding principle than something that we would like to understand completely in our lifetimes. Okay, so Selberg class consists of all meromorphic functions Fs which satisfy the following properties. Okay, so the first property is they have a Dirichlet series. Okay, so this is again what we saw with the Riemann zeta function, right, where AFN was just 1 for all n, and with Dirichlet L functions, it was chi of n for all n. And we can, of course, normalize it in such a way that it makes there are various ways of stating these axioms or these requirements. You could say that this is absolutely convergent for real part of S sufficiently large. Okay, so there's some line on the complex plane, real part of S equal to 7 by 8 or whatever, or 17 by 3 or something like that. At some point, and then it converges beyond that. But if you have that, you can normalize these AFs in such a way that you get absolute convergence beyond a real part of S bigger than 1. Okay, so often when people talk about L functions for elliptic curves, the natural way to state the Dirichlet series makes it convergent beyond 3 by 2. Or if they talk about L functions of modular forms, the natural way to state it makes it convergent beyond k minus 1 by 2, where k is the weight of the modular form. Okay? But anyway, this is the first requirement, and we saw this with both zeta function and Dirichlet L functions. The second is Euler product. So Selberg demands that this Fs has Euler product. Again, the Euler product should make sense beyond in some right half plane. So we have normalized our things so that the right half of the complex plane is real part of S bigger than 1. Okay. It should have this Euler product, and we saw that this was exactly the kind of Euler product we had for both Dirichlet L functions and Riemann zeta functions. Okay, The third is it should have meromorphic continuation, except possibly poles at s equal to 1. Okay. Now of course, I told you that this condition holds for, and in fact I sketched a proof that this condition holds for zeta function, Riemann zeta function. But if you are seeing this for the first time, or even if you're not seeing this for the first time, but you haven't spent a lot of time studying these things, this might seem like a very mysterious thing. Why should L functions have pole only at s equal to 1? Um, and the reason is kind of very deep and maybe not worth going into right now. But if we want them to come from some geometric objects, then this is they should always have this property, that they should be analytic everywhere, except possibly at s equal to 1. Okay. And these things, and even for things which come from geometry, these things are very hard to prove. For instance, there is a conjecture of Artin that Artin L functions of non-trivial characters are analytic everywhere. Okay, they have no poles, and that's still an open conjecture. And the whole Langlands program was conceived by I mean, it started with Langlands trying to understand Artin's conjecture about analyticity of Artin-L functions. Okay, so this three is kind of mysterious, but it's once you spend a lot of time doing this is natural. Okay, then there should be some functional equation. So let me not spend a lot of time trying to say what this is, but basically you just don't have fs and f1 minus s. You have to multiply it by a bunch of things like powers of pi and powers of 2 and some gamma functions and so on. uh, but yeah, rather than sort of saying what precisely these alpha i's and beta i's and so on are, let me make the following comment. Okay, so we learned about the Euler product, right? So Euler product is product over all prime numbers. One should think of this mysterious, this thing q to the s and product of gamma factors as an Euler factor at the infinite prime. So what that means uh, is that uh, later on I'll say a word about p-adic numbers. And so you can yeah, so from q you go to p-adic numbers qp, but with the usual metric on q, so with the usual notion on distance on q, when you take the completion you get real numbers, right? So this point of view puts prime numbers and real numbers on the same footing. So one should think of this as a factor coming from real numbers rather than prime numbers. Okay, so one should think of this as a factor that comes from infinite prime. And so from that point of view, it is not at all mysterious that the right L function is the one with this factor for infinite prime, and not just the Euler product with finite primes. And so that's why this has the functional equation. So bar here simply means complex conjugation, and W is some sign. It's either plus or minus 1. Okay, and then there's the Ramanujan hypothesis, which of course did not show up explicitly in Riemann zeta function, because these were all ones. So it means that these don't grow more than e to the epsilon for n to the epsilon for any epsilon. Okay, so what this means is, this big O notation simply means that for any epsilon greater than 0, there exists a constant such that an, the absolute value of AFN, is bounded by that constant times n to the epsilon. Okay, yeah. So again, these things can be quite hard to show for the actual L functions that one is interested in. Uh, Right. Okay. So why are we looking at the Selberg class of L functions? Well, as I said, from my point of view, these are supposed to. I mean, conjecturally, these should capture all the interesting L functions. Okay. Now, of course, there are other Dirichlet series which have no Euler products and so on, but maybe they are not as interesting for me as these. So uh, for others they may be more interesting, right? So there are Dirichlet series people define in group theory which may not have Euler products and so on. So um, yeah. Anyway, so those are not captured by Selberg class cell functions. Roughly speaking, what I mean is that when I say these are supposed to capture all interesting L functions, is that anything which satisfies this should come from a automorphic L functions. Automorphic L functions. So there are things called automorphic forms, which are basically generalizations of modular forms, and so any L function like this should come from an automorphic L function. So there is a way to attach L function to automorphic forms, and uh, so given any fs in Selberg class, there should be an automorphic form whose L function is this fs. Okay, and in some cases, people can actually prove these things. These are what are called converse theorems. Okay, so these started with Andre Weil, and there have been many versions of converse theorems and many generalizations uh, of converse theorems. Okay. Uh, yeah. So as I said, often it is very non-trivial to show that an L function coming from geometry uh, lies in S in the Selberg class. So I'll mention two examples. Uh, One now and one later on. Um, yeah, the first one I already mentioned. There's a generalization of Dirichlet L functions which are called Artin L function, and it is still unknown whether all Artin L functions are in the Selberg class. Okay, so it's been about 100 years since Artin defined his L functions, and we still don't know basic things about them, whether they are entire apart from s equal to 1 and so on. Okay. And let me come to some applications of L functions. These are very vague general sort of applications of L functions. Uh, yeah, so analytic properties give you distribution of arithmetic objects like prime number theorem. So you may have heard about this, or you can easily read about how the most natural way to think about prime number theorem is in terms of zeros of the Riemann zeta function. Okay, so you can express prime number theorem in terms of what is called this Van Mancolt function, and you can relate the logarithmic derivative of Riemann zeta function to this Dirichlet series with Van Mancolt function, and so logarithmic derivatives of course are related to zeros of the function. You can kind of almost think of it like a polynomial, and so if you take polynomial of if you take logarithmic derivative of a polynomial, uh, you can easily relate that to zeros of the polynomial, and similarly you can do it for analytic functions. So that's how you relate prime number theorem to analytic properties of zeta function. And this is not true just for Riemann zeta function, right? So for all these Selberg class L functions, you can relate distributions of certain arithmetic objects, wherever the Selberg L function comes from, to analytic properties of that L function. So so there are results in sort of various kinds. So if you you can either just pick an L function that you are interested in, the L function of an elliptic curve, and you can say, well, if I want to understand distributions of these things on elliptic curves, can I deduce it from L functions? So there are results like that. On the other hand, there are also results which say that analogues of prime number theorem hold for Selberg class L functions. So these are results of Murthy, for instance, that one can look at. Okay, and okay, so one thing I mentioned was values of the zeta function at negative integers are rational numbers. Values of the zeta function at even positive integers are powers of pi times rational numbers, and these rational numbers actually mean something. They have some arithmetic content. Okay, and these are again and this is not true just for zeta function. This is true for this whole class of L functions, Selberg class of L function. For example, the famous Birch-Swanerton-Dyer conjecture is about value of the L values of L function at s equal to 1, values of L functions of elliptic curves at s equal to 1. Okay, so this is the second kind of application. These are very broad applications and not exhaustive list at all. I'm just giving three things that kind of maybe I understand something about, or to think about from time to time. The third application is kind of, it's not doing justice to this by putting it this way, but it's used for bookkeeping in Langland's program. So Langland's program, it gives you a bijection between two infinite sets. Okay, and that's kind of meaningless, right? If I'm giving you a bijection between two infinite sets, all I'm asking is that their cardinalities are the same. So that kind of can't be uh, very useful, one would think. So what Langland's program says is that here are these two sets. You can attach L functions to both, and the way to associate an object in one class to the object in another is that their L function should be the same. So that's what I mean by they are used for bookkeeping in Langland's program. But of course, they are so much more. They are so much more fundamental to Langland's program than just bookkeeping. So, but this is the most concise way of putting it. Okay. Now we go back. Yeah, before I go back to our favorite L function, the Riemann zeta function, let me give you two more examples of L functions. Since I've mentioned this whole Selberg class of L function, it's only fair that I give you more examples. Okay, so elliptic curve. So elliptic curve is basically defined by an equation like this. So if you don't know what an elliptic curve is, you don't need to worry. I'm just taking solutions to this equation. Um, and this is a condition to say that what I actually end up with is an elliptic curve, in the sense that the curve I have does not have any singularity. Okay. Now, for a prime P, what I do is I take all solutions in Z mod PZ, right? So all elements in U comma V in Z mod PZ square, which satisfy this equation. So I count how many there are. There are, of course, finitely many. I subtract it from P. Okay. Another way of putting it, which is a more standard way, is this one. So P plus 1 minus the number of points in EFP. Now, why is there a plus 1 here but not here? Is because this is only looking at the affine part of it. Okay, I'm not looking at the point at infinity. There's a unique point at infinity in the projectivization of this elliptic curve, and so yeah. So this is kind of a very hands-on thing. If I give you any values of A and B and ask you to compute AP for all primes less than 1 million, you can just write a short program and make a table of it without knowing absolutely anything about elliptic curves, right? So that's why I gave the first one. The second one might need you to make to look into some books about what exactly that means. All right. I will normalize it in some way. So a tilde p is a p divided by square root of p. Okay, so it's a famous theorem of Hasse that a p is actually between uh, minus 2 times square root of p to plus 2 times square root of p, and so I'm just normalizing it in some way. And this is the L function. Okay, so I define it using the Euler product like this. Okay, now of course I told you when I started saying something about the example that this indeed lies in the Selberg class, but that is highly non-trivial. Okay, so this we knew this in this generality. By the way, I should have said where a and b lie. A and b are rational numbers. A and b are integers. Okay, sorry about that. Yeah, a and b are integers. So it was finally established that this lies in the Selberg class only after Wiles proved the Taniyama-Shimura conjecture. Wiles and his co-authors, right? The full Taniyama-Shimura conjecture. The other thing is this Ramanujan's delta function. As I said, this again is explicitly defined like this, right? So delta of z is q times 1 minus q to the n to the 24, where q is e to the 2 pi I z. Okay, and one can expand this like this. So this is how tau n is defined, and Ramanujan wrote a lot about this tau n. Right? So all right. So again, I normalize it in some way, and you define the L function like this. Okay. So again, this is supposed to lie in Selberg class, but this was only established completely after Mellin proved his Weyl conjectures. Right. So very non-trivial, even in very classical examples. So both, I mean, Ramanujan's delta function is over 100 years old, and elliptic curves were studied in 19th century also. Right? So okay, but yeah. So this is the second thing I wanted to say about class, like difficulty in showing something is in Selberg class. Okay, now back to zeta functions. As I said, the values of L functions at integers, these are called special values. Okay, so that's the term that's used in this field. Special values or special L values. They have remarkable amount of arithmetic information. Okay, and one gets hold of this information through what are called P-adic L-functions. Okay, now of course I'm not going to tell you about general P-adic L-functions, but I'll tell you P-adic nature of these values for a Riemann zeta function. And what I mean by P-adic, I'll try to explain now. So for simplicity, from now on, I'll assume that P is odd. Okay, if P is equal to 2, I just have to modify it somewhat. Okay, so P-adic properties of zeta values. Now I know that the zeta of minus n is a rational number. Okay, what Kumar proved in 19th century was that zeta of minus n is congruent to zeta of minus m mod p. Now, of course, you must have seen this notation for integers, where what it means for a to be congruent to b mod p. It just means that p divides a minus b. My zeta values are not quite integers; they are rational numbers. So what does this mean? This means that if a and b are rational numbers, then a is congruent to b mod p means that a minus b, when I write it in the lowest fraction form, meaning I write it as q over r, where q and r are co-prime, then q is divisible by p. Okay, so the numerator is divisible by p. Right, so that's what it means. Right, so he proved this. This is called Kumar congruence. So this is quite remarkable that if n and m are congruent modulo p minus 1, then the zeta values at minus n and minus m are congruent mod p. We have to stay away from this class minus 1 for for some technical reason. This is related to the pole at s equal to 1, but I'll not try to say how exactly. More generally, Kummer's congruences were about 70 or 80 years later, after Kummer, were generalized by Kubota and Leopold to the following thing. So again, you have to, this hypothesis is still there, that M is not congruent to -1 mod P minus 1. But if you have N and M, which are congruent not only modulo P minus 1, but P to the K times P minus 1, then zeta of minus N is congruent to zeta of minus M modulo P to the K plus 1. So you get a better congruence if your N and M have better congruence to start with. So this is quite remarkable that not only these things are rational numbers, but they are not random things. They actually are related to primes in this way. Okay. So let me give a very quick introduction to p-adic numbers. Okay, so what I do is I define a p-adic metric on integers. If I have an integer a, then I write it as p to the r times b. Okay, where p does not divide b. Then the p-adic norm of a is defined to be p to the minus r. Okay, so the more this integer a is divisible by p, the closer to 0 it will be. Okay, so if p is equal to 3, then 3 is closer to 0 than 1, and 9 is closer to 0 than 3, and so on. Okay, so I can define distance between two integers a and b as the p-adic norm of a minus b. Okay, so yeah, so this is just like the usual modulus, but it satisfies the properties of usual mod, like mod of x, but now this is defined in a different way. Okay, you must, this is what you see in the first course in analysis that one takes at university, completion of rational numbers to give you real numbers. Now you can complete your integers with respect to dp, and what you get are p-adic integers. Okay, so this is a very quick thing. So -1 in this thing can be written like this, for example. Okay, so this is a p-adic number, and this is also a p-adic number, and -1 becomes this. So this, of course, does not make sense. 1 plus p squared plus p cubed and so on. That sum does not make sense when you are over real numbers, but that sum makes perfect sense if you are over p-adic numbers. And when you multiply that with p minus 1, you get -1. So formally, of course, you can just think of this as a geometric series, and you get 1 over 1 minus p, and so you get -1, right? So that formal thing actually makes sense in p-adic numbers. Okay. Yeah, so of course, if you complete z, you get zp, which means that z is dense in zp. Not only that, negative integers are dense in zp, and because our p is odd, actually odd negative integers are also dense in zp. So this is what I'm going to use on this next slide. Okay, so again, as I said, for simplicity, p is odd. Then Kummer congruences, they imply the following. I have this function which goes from odd negative integers to rational numbers. So why am I leaving out the even negative integers? Well, at even negative integers, the zeta function is always 0. And so it's taking value 0 at infinitely many things, and that's not, I don't want that. Okay, so what is the function? It takes an odd negative integer to this zeta value at that odd negative integer. Okay, so this is a well-defined function. But what Kummer congruences tell me is that actually this function is continuous with respect to dp. Okay, so yeah, I did not say how to extend dp to q, but it's in the obvious way. Now there's a metric dp on both sides, this side as well as this side. And what Kummer congruences tell you is that this function is continuous with respect to dp. And so you can show that you can extend it to a function from zp except at 1 to zp. Okay, and this is what is called the p-adic zeta function. Okay, so this is the p-adic zeta function. This is a p-adic avatar of the Riemann zeta function. So Riemann zeta function is a complex zeta function, and this is the I would call Riemann zeta function the complex zeta function, and this is the p-adic zeta function. Okay, again, it's not defined at s equal to 1. It has a pole at s equal to 1, um, a simple pole at s equal to 1. Okay, now of course this is not even a complex analytic function, right? This is very far from complex numbers. This is in p-adic numbers, so this does not fit into Selberg class of formalism, the Selberg class formalism. So I was lying through my teeth when I said they include all the functions that I care about. I of course care deeply about p-adic L function and p-adic zeta function. But what I meant there was the Selberg class L functions contain all complex L functions that I care about. And now here's a completely new class of L functions that I want to introduce you to, which is the p-adic L functions. And so, of course, I wouldn't tell you about a general p-adic L function, but only that there's this p-adic avatar um, of the zeta function, and it's defined in even more mysterious way than the Riemann zeta function. So Riemann zeta function at least has this very nice series representation in the right half plane, and then there's this mysterious extension to the whole complex plane. The p-adic Riemann zeta function is defined through these values of complex zeta function at some points, and then you say that you extend it to the whole p-adic plane, so to speak, right? So it has even more mysterious definition. Now, just like Selberg class just like for complex L functions, um, for just like for complex zeta function, you have this whole theory of Selberg class L function. Also for p-adic zeta function, there's a whole conjectural theory that every complex L function that comes from geometry in some sense should have a p-adic avatar. And many of these have been constructed, many have been very fruitful. All the development on Birch-Swinnerton-Dyer conjecture that has happened in the last 50 years is because of the p-adic avatar of complex L function for elliptic curves. Okay, so these p-adic L functions, they are closer to arithmetic than complex L function. This is at least what our experience is. And so they provide an intermediate path to go from complex L function to arithmetic. So these are yeah. So this is my answer to what are L functions. So the L functions, the what answer to what are L functions for me is Selberg class L functions, and on the complex side, and p-adic L functions on the p-adic side. Okay, I'll stop here. Thank you.